workflow is, what the software is associated with that workflow. We're going to take you through bit by bit in what I sort of call follow the bouncing ball type exercises through the whole workflow. And then right at the end, the lease sale is meant to build up or sort of via repetition in a more unstructured, in a less structured way, what this particular workflow is. But also we've tried to make it fairly realistic to what you end up doing in an everyday basis when you're faced with a property. I want to get some volumetrics because I have to go and have input in either in terms of a lease sale or a particular evaluation of a particular property. Okay, and we do that all the way from the beginning petrophysics all the way through to the final risks that you can and volumes that you can enter in to an economic spreadsheet in order to find out what the value is of the property. And that we've always started with particular introductions in the previous courses to both help Dave and I as instructors sort of understand different people's backgrounds, but also to introduce us to each other because I think a large portion of this too is going to be networking. As you'll see that there's some people from the minerals side as well as a good cadre from the petroleum side, and to help sort of build a particular community around sort of quantitative interpretation. And that, first of all, that Dave DeMartini and myself are going to be the instructors for the course. That our bios are at the back of the large manual if you end up opening it up. If you want to find out sort of more details, about us, I think it's the last thing in the book here, and it's also out on the website. Just sort of quickly in terms of where I've sort of been in the life, that my background is I started with Shell Oil after I got my bachelor's in physics from Case Western Reserve. I worked for them in the Rocky Mountain Division doing near-surface refraction statics, for those of you familiar with that, as well as working in some early versions of 2D Kirchhoff pre-stack migration and the application of it and some of the pre-processing for that. I then got my PhD in theoretical physics from the University of California, and that was actually in plasma physics. Did a postdoc at Lawrence Livermore National Laboratory. Came back to Shell Research, focusing primarily on probabilistic inversion of seismic data. Also got a little bit into economics, petroleum economics at that time. I started with came over to BHP in 2000, where I ended up leading the quantitative interpretation effort until early this summer, where I've now moved over and part of the Resource Business Optimization Group. We're currently at the Perth Technology Center, but I think before the end of the year we'll be moving into this building on the 36th floor. And the particular focus now is going over towards mining, even though I'll have some particular continuing contact with the petroleum company. Our remit is around resource estimation, methodologies for doing that, and that's sort of reserve estimates in petroleum parlance. And so the stuff around, probabilistic inversion, the like, that you'll see, and even the things that we're talking about in this course, that the particular focus is probably going to be a little bit more balanced corporate-wise in terms of, more closer to the division between mining and petroleum. But again, I think that there will be, continuing interaction as warranted. And anyways, I wanted to go and then sort of turn the floor over to Dave, and then we'll sort of go around the room. I think that the least, make sure you say your name, where you're working right now, and what you really sort of hope to get out of the course, and what your current job assignment is. Dave?
Yeah, my name is David DeMartini, and I did my academic work in physics at the University of Notre Dame, bachelor's degree, and then PhD at Ohio State, and worked for Shell Research starting in 1969 for almost 30 years. That's where I met and Mike, worked with him there, and at the end of '98 I retired and from Shell, and I'm working for myself now, Lone Star Geophysical Consulting.
Okay. We'll start back. If you look at your desktop, there should be a link on your desktop right here. These two other links have to do with the exercises, and I'll explain that when we get to it. But right now, though, if you end up clicking on the quantitative interpretation link, that's probably on the other side. That is a password, yeah. That here is the particular website. If you go to lectures, that you can go and click on any of the lectures, and it should bring up a particular PDF of that lecture. Also all the information with respect to the exercises, it's in that small packet, or you'll find on the second page. Dave and I will refer from time to time to different supplements. These are not in your manuals, and you can go and find those at this particular one. I do talk about other places that you can go from time to time, and there's sort of these links pages. And then finally, our biographies are on the last one. This is also available in a password protected way outside of the firewall. And if any of you are interested in getting access to that, I can give you the link and the password for that to be able to get access to it external to BHP. Okie doke.
So this is a proprietary course, right?
That is right, yeah.
And we want to keep it that way, or?
Yes, I mean, there's, with respect to the data that we're using in the course and the like, the particular workflow, I mean, be honest, I mean, I think that you can go down the street to Down Under and that they'll, go and, help you in terms of the implementation of it. And so I would say those particular parts, no. The particular things around the beginning that Dave has put together, that he's gone and retained copyright on that in terms of giving it, in terms of outside of BHP. We do have the ability to freely distribute it within BHP and to give courses off of the early parts of the material. But we have not gone and don't have general release on the latter part. And also the lease sale exercises are South Africa acreage, which has not yet been drilled. And so, and also is data that's proprietary to BHP. And also we have some of the more advanced data over Sty Barrel, even though certain parts of that are coming into the public domain. So yeah, it's generally you don't want to go and distribute it outside the company. Is kind of the bottom line. Then let me go back here to the particular presentation material, and we'll go and start the main part of the course. Let me get my thing to advance the slides, just so you can see me as I sit over here. And I sort of had gone in the particular title of the course that we have is sort of quantitative interpretation BHP style. And you'll see as I go through this, from time to time, I'll talk about some things which are, probably unique in terms of the standard workflows you would see with respect to amplitude extraction to what BHP does. Then to sort of warn you that if you're talking with people on the outside, some of these, at these particular points, people will probably look at you with a little bit of a blank stare from time to time and might take some extra explanation. As Tom, though, said that those of you that have worked within the Shell empire will probably be much more comfortable, and it's probably the place in the industry where you'll find the workflow closest to what's going to be presented here. So if you're going in and working here locally with Woodside, that many of the things that you would go and talk about here, they would sort of comfortably understand. And I sort of gone here and have said sort of what the particular definition is that we're using of quantitative interpretation. That originally the group was called lithology and fluid prediction, and I ended up going and having a bit more of an expansive definition, and is one that I think is going over and transitioning very well into the minerals resource estimation and not only the petroleum reserve estimation. And we're talking about the synthesis of three predominant types of information. You can include more types even than this, but these are the primary ones. The first is remote sensing at seismic. That, for those of you familiar with it, doesn't have very good vertical resolution, but has very good sort of lateral resolution and coverage. You have E&M methods, which don't normally have very good lateral or vertical resolution, but have independent estimates of things like resistivity that can help us with sort of known pitfalls like low saturation gas, which can go and have good seismic reflectivity, but not very good resistivity. And so you can like tell the difference between that and full saturation gas using different E&M methods. For the mining area, that's actually something that's been in use for quite a while, and probably much more extensively used than the petroleum area until just recently. Then finally we end up having well logs, and these are the ones where we don't have very good lateral resolution. Normally it's sparsely sampled, but we have very good vertical resolution. And I think that the particular challenge many times in the mining area is how many wells do you have to drill in order to sort of prove up the resource. And I think some of the particular sort of interest is, okay, how do we go and determine the minimum number of wells and play that off against seismic that can help us fill in the blanks. And especially for the potash area, that is, I think, coming to the fore. But you want to go and combine these measurements together to have an integrated estimate of the risk and uncertainty. And the uncertainty is around resources and or reserves, as we would call them in the petroleum area, and in a way that's suitable for making business decisions. Okay, and that's really where we're going to come about in terms of the lease sale example. When you know what the probability of success is, or how large or small the volumes are, those now can be put into your economic models and help you in terms of your decision trees in making business decisions. And it's one thing that I've probably been talking about as we've been going through our goal setting in the RBO, is that going and having a measurement, going and doing technical work has no value unless you influence decisions. And so we need to go and get this information in a form that can influence the business decision making. And the primary methods that we end up employing in order to combine this together and get these uncertainty methods are Bayesian based. It's a person based. And people throw that out there, and normally if I'm in any management meeting, they immediately put a red pen through that word and say you can't use it. Okay, fine. But if you go and ask what it is, and we're going to have sort of a lecture around this, it's really just a probability commutation relation, flipping the ordering of a conditional probability. A, what's the probability of A given B? Okay, and that's all it really is. Okay, it's not. I sort of hesitate to even sort of use the label on it, but that really is what underlies these techniques. And the reason why we do it is it's a good way to integrate data that have these different type resolutions, and then also go and propagate what the uncertainty is. And that's, I think, one thing that we're now, when we get to sort of BHP style, is that the particular, what borders on the obsession with uncertainty and the estimate of it, is something that you'll find is, it can be a bit different than what you'd experience other places in the industry, where I think that many other people tend to focus on the most likely result, not what the ranges are. And also, as a note, that we aren't going and throwing away the geology, okay? That this comes in as a very important number, and even in terms of Bayes, the equation, that there is a very specific place in there where geology enters, and they're called the prior probabilities. And so that's where geology and the petroleum systems information is integrated in. And when we get to the section on the risk estimation in our risk spreadsheet, you'll see where those specific risks that come out of this type of analysis, the reservoir probability, the chart, source migration timing probabilities, explicitly get taken into account and get combined with the information, the remote sensing information, and the well log information that we're bringing in. Okay? Any questions at this point? Okay. Go and hit next. We ended up going and getting together with the vice presidents of petroleum and asked them what were the particular aspirational goals that they wanted for quantitative interpretation. Because we wanted to understand what the commitment was, what the senior management level sort of view was of where they wanted to go. There are a reasonable number of words here, but the first thing is that they felt that having this type of technology and influencing business decisions does give us a significant competitive advantage. And you'll see some examples of that in the next couple view graphs. And that also the focus is on risk and volumetric uncertainties using Bayesian methodologies, which is sort of in the overall sort of first all definition statement I had. And that it should be integrated by a combination of consultancy and training of the asset staff. And that's really was saying that, hey, I should be giving this course is the other part of it. But it also means that we should have a strong internal mentoring of the capability. And that go and only develop stuff where we can't find something commercially. But you also see that the particular software and workflow that we sort of embodied here is sort of part and parcel of being able to estimate the risk and uncertainty. And in the end, that we should do this well enough that we really can base business decisions off of the outcomes of this, and believe it enough to say that we don't have to hit the reset button and say, no, you've done all that work, but I just don't believe it. Okay? Because you need to go and have a good understanding of it. It needs to be transparent what's being done from beginning to end so that you can base a business decision off of it. In fact, one thing I've seen here in the office, and one of the nice things about having a lot of this stuff in spreadsheets, if you don't understand everything, dig into the spreadsheet, okay? And go and change the numbers, right? Because I remember it was kind of interesting after the first time I gave this course, someone who was working with the risking spreadsheet and sort of said after they were playing around with it for a while, that changing the seismic quality really matters. And so, but that actually ends up being a very profound statement, because they ended up realizing that one of the most sensitive things they could do would be to go and ensure that they had the best processed data from Dark Vader here in terms of getting the best things out, okay? But I think that you'll probably note, though, even though I do kid a bit, that I really do have a deep respect for seismic processing and making sure that it's done right. It's a very important job, and we can't do the particular high-quality quantitative interpretation, though, without it. And you'll hear me talk about that for a bit. But first of all, let's sort of talk about what we mean in terms of estimating and reducing risk, okay? And that we start off many times with sort of the standard geologic risking, and that we'll go and put that in terms of reservoir probability, the probability of charge, source, migration, timing, And we end up dividing that between things that you can that you care about in the end. What's the probability that you'll just find a wet sand? What's the probability you'll find a shale? What's the probability that you'll find a sand with gas in it? And obviously things that you like are gas and oil, and many times you like oil more than gas. In the Gulf of Mexico, they both have about equivalent value. But then if you go in and add this remote sensing information, what happens to the risk? And many times we've called that sort of the DHI boost in the petroleum division. It really is a Bayesian update to these probabilities given the measurement. And you'll see that with phase one, which is the predominant workflow that we're going to be talking about here, I do have a lecture at the end where we talk about phase two and the particular assumptions that you don't have to make in phase two that are made into phase one. And you see that you go, and the probability in this case of the things that you wanted ended up increasing. That means the risk was decreased, which means that you'd pay more money for it, or someone would have to pay you more to buy it off of you. Then if you ended up using the more complicated phase two methodology, you see that the risk is reduced even more, because it ends up having less assumptions, it looks at more information, and therefore reduces the risk more. So not only going in phase two, though, do you go and relax some of the assumptions of phase one, which I'll talk about, you also see that because it brings into account more information, such as what is both the top and base reflector, not only what is the reflection strength, that it can go and have the ability to reduce the risk even further. Okay, then you'll say, well, okay, yeah, you have numbers there. Well, so what? Are they right or wrong? Okay, how can you tell? And this is in something that you always need to do is to go and look back at what your particular historical performance has been. From the period of 2000 to 2005, when we were drilling a reasonable number of wells in the petroleum division, that we ended up going and having, this was the prediction of the 22 wells that we drilled, how many successes we should have. We had probabilities. You had to go and put a Poisson distribution around those probabilities, and that is what the probability of having, let's say, 10 successes out of the 22 would be. And we ended up having 12, which is very close to the most likely number. And we also tore apart the statistics in more detail and found, that we were consistent in terms of, even in more detailed ways, in terms of what our predictions were. But this is a very important thing, is to periodically go, do the look-backs, making sure that there isn't a bias in your system and that you're doing things correctly. But then, and this is not really the particular case with respect to our competitors, that if you go and take a look at, this is a slide that was shown in SEG lecture given by a person from Exxon. And what they ended up finding here is that if you go and take a look at stuff that they ended up ranking at about a 70% probability of success, it turned out that the probability of success was really 97%, okay? If they went and said it was 30%, okay, they ended up being that it was ended up being less than 10, was right around 10% probable, okay? And it's a fairly common thing in industry, and it comes about, and I sort of like this graph, which ends up showing, first of all, the probability of success as it was predicted versus how many times that you end up having that, okay? Our particular distribution in this look-back study was fairly uniform, going from fairly low values all the way to fairly high values. And that the particular information we can get with respect to our competitors from things like this previous view graph show that their distribution looks like this, okay? And this actually is not an accident. There is a particular, I sort of have a guiding sort of theorem behind what causes this, okay? And it's based on the theory of minimum management accountability, okay? And you say, well, wait, how does that lead to this, right? Well, let's look at it a little bit more carefully. Okay, the most likely value is 30%, okay? There's an expectation of failure. So if it's a success, you have a modestly pleasant surprise, but you did say it was reasonably probable. What happens if it's a failure? Oh, you said that, hey, I said it probably was a failure, so that's the particular expectation, okay? And it also turns out that if you go and do a statistical study, it's when you go and predict something around, let's say 30 to 50 to 60% probability of success, you have to drill the greatest number of wells to prove that you were wrong, okay? Okay? And so, in other words, it goes and takes the longest period of time in order to prove that you weren't predicting correctly. And normally, if you take a look at the number of wells, it equals about, in order to prove that you're incorrect with this prediction, you have to drill about the number of wells that most people will drill in their careers. So that by the end of your career, you can prove that you were probably giving wrong predictions. But by that time, you collect your retirement, and there really is not a whole lot of accountability. But sort of joking aside, I really do think that this sort of drives this particular conservatism. But then you say, well, so what? Okay? Well, if they really do believe this, right, that if we go and assess something up here at this high probability of success, if they think that's the probability of success, we can buy it for more than they think it's worth, but a lot less than what it's actually worth, if we're correct. And also vice versa, okay? I sort of say, buy from the sucker, sell to the sucker, in terms of, where, the particular business opportunity lies, okay? And so this is where you can translate risk into business opportunity. There's another thing where you can get into a little bit more detail, and this is sort of going downstream a bit. And this has to do with the uncertainty, not the risk. Here is the probability in the success case of having a certain amount of resources or reserves that you can exploit, okay? And we end up giving a range of what that probability is. Nothing to notice, it's asymmetric. It has a long tail here on the high end. Another thing is that if you go and give sort of a basic estimate of what most people do in the industry, so the non-BHP do, they just give a number, okay? But really, one thing that I learned, and you'll probably hear me repeat again, as a young whippersnapper physicist, is the measurement is useless. It has no value without its uncertainty, okay? Because if I go and predict 100 and I find 106, is that good or bad? I don't know. If your uncertainty is 0.5, that's bad. If your uncertainty is, something like 5, 10, it's probably an expected outcome. If your uncertainty is 20 and you always end up within 1 or 2 of the right answer, also, that's not good, okay? Many times you'd say, hey, that's good, you're always right on. But if you were predicting a larger range, that's not good. You say, sort of why is that the case? Well, many times particular business decisions are around risk tolerance. We write a contract to deliver gas, okay? And we have to make sure that we can deliver on that contract, and there's a fairly high probability of delivering on that contract. So we'll say that we have to make sure that we can go and we have a 90% probability of having that much resource or having that much reserve in that particular field. Or many times managers will say, look, I want to make sure that if you look at the economic threshold where you can produce enough to recover your initial capital investment, that I can at least break even on this project, and there's a fairly high probability of breaking even. And unless we have this particular distribution, there's no way that you can go and make those decisions. And in fact, in terms of acquiring information, at the point that you end up sort of getting this sort of P90 above your decision threshold, is sort of the particular point at which you should stop acquiring data. And you should go, in this case, if you're worried about where the P90 is, acquire the data that can, as quickly as possible, bring you above, your particular decision threshold, okay? And then let me go, and I'm going to click on another thing, which is sort of where is the well? Well, where is the field? Okay. What you're seeing here is where the particular hydrocarbons could be in this oil field, and the color is sort of how thick or how much you may find at that location. Okay. And now, okay, where do you drill the well when your field is moving around? Well, actually, the field doesn't move around. The problem is that because of the steep dips here, you didn't know where the particular field, where the image could possibly be misplacing it. Okay. And that, if you go and, let's say, would drill a well at this location and have an outcome, you now can ask, okay, first of all, what's the probability of hitting the reservoir? But also, after you would go and drill a well in this location and say not find anything, would that have value? You say, well, you drilled there, didn't find anything, that doesn't have value. Well, actually it does, and this is after a well was drilled there and you didn't find it, you see that the uncertainty about where it was ended up being reduced. And it turns out that up dip is in this direction, and if you end up drilling a well here, you can only produce the stuff to this side of it. So the thing that you want to do is to place the well as far as you can on this side in order to be able to drain the largest amount from that field. So reducing the uncertainty of where that is ends up being paramount to be able to, with confidence, drill a hole which is as far up dip as possible. And so this is getting more into the details of how you exploit that resource. But again, it's sort of pointing to what's the value of the uncertainty as it goes back to the value of information. Okay. Have things been pretty clear to people as I've gone through these couple examples? Or? And then finally, this is the Scarborough field. Those of you that, in fact, have either worked on it or a sister field, or we're actually going to be shooting a CSEM experiment over this. And that this is really going into some of the phase 2, again, methodology. But you ended up having, in this case, sort of estimates before we came into quantitative interpretation that ended up having a range and also, a most likely. But the particular problem was that the minimum economic field size ended up being at that location. And people wanted to go and see and get this above that level. And we went in and went through the particular workflow. The distribution came out to this, and you ended up going and finding there was a fairly high probability of being above the amount of reserves that you needed to have in this field. It was kind of interesting, and it's a longer story, and it's more involved in this in terms of everything that ended up causing the shift. But in the end, there was a real nice give and take between the reservoir modeler, Mark Woodall, and the QI team. And in the end, we became very comfortable with the distribution that you saw here. But to understand though that yes, was this important? Well, we ended up having people call us from senior management on almost a daily basis, and we had to almost say, look, we have to work through the details. We could tell you, our particular opinion today, but we don't want you to see, but this is going to go up and down, and wait until we can settle. But the fact that they were calling up, on a daily basis saying, do you have an answer yet, means that it really mattered in terms of the decision that they were going to make. And also, we ended up making sure that we could embed it in a Petrel model so that it could be used in the reservoir simulation. And this is sort of equivalent, Jeff, in terms of GoCAD, that we ended up doing the inversion, and then embedded something into what's sort of the equivalent of a GoCAD model. Okay? And here you end up seeing that we were actually looking at some details of the uncertainty associated with the model at a particular location. But I'll get into that in, I think, lecture 12 when I talk about the phase 2 in more detail. But you really want to go and just take a look at the fact that the uncertainty matters here in terms of the definition. So now let me go in and I'll talk a bit about what the workflow is. And right at the end, then we'll go and it'll be, I think, tea time. and we can then go down, those of us who need to get an induction can get that. Okay, what's the logic of this workflow? Okay, and you're going to see this view graph quite a few times, and it's really fairly simple. Okay, first of all, go and predict what you should see is the lower range. We look at sort of regional predictions that come from looking at well logs. We predict what the expected seismic response should be. At the same time, we look at, okay, what the response is. Okay, we take the seismic, we make particular amplitude measurements off of that. We make sure that we use the well logs to calibrate the seismic. And then we go and compare the expectation to the measurement. And from that, we can go and make a prediction of what should be there. Okay? And so just go ahead.
So on the well log phase, is that where you do your ex-Gassman fluid substitutions?
It's down here, yeah. It's down here, yeah. Then we'll go and do a bunch of Gassman fluid substitutions down here in order to predict what we should be seeing. Yes. And we'll get into that in actually quite a bit of detail. We're not going to go through a derivation of Gassman. We'll talk a lot about the implications of Gassman and where it fits in. And in fact, what we do is we start with these petrophysical relationships. This is the bottom branch. We go and look at correlations that show things like this is the compressional velocity versus density. This happens to be for sandstones, and this is for shales. And you ask, why is this cluster different, right? And it really happens because for a particular density, you end up seeing there's a much higher compressional velocity for the sandstone, which means it's more competent. It's very efficient at getting rigid for the stuff that you put in it, okay? And this is not, just specific to petroleum, okay? That I think that the particular challenge is like for potash, for coal, is to understand what these particular type of basic relationships are. That then leads to the second thing, which is what is the expected amplitude, okay, or AVO behavior that you expect given a shale to shale reflector or a shale to brine sand reflector. You see the most likely and as well as the uncertainty. Then we go into the seismic data, which is the upper branch, and we measure amplitudes, and we'll have a whole lecture on how we measure and extract those amplitudes. We compare these extracted amplitudes to the predicted amplitudes, and from that you can get what the probability is. And then also by looking at the amplitude as well as the thickness or the area, you can get an estimate of how much stuff is there or what your resource is, okay? So again, what it is you predict, you measure, and you compare the measurement to the prediction.
So on that amplitude chart, upper right, that is based on the ex-Gassman fluid substitutions, right? This is what we expect when we fill the rocks with shale, brine, oil, gas, right?
That's exactly right. And the uncertainty, and then we're putting it into a sandstone of the expected compaction stage.
So you model.
Yeah, we'll get into the gore of that in very specific detail of exactly how we do that and what we allow to do.
A little confused on the term boost. But,
well, yeah, that's more historical. I came into BHP. There's a certain dictionary they have, and they always talked about, what is the DHI boost? Given the amplitudes, how much do you change the probability? Okay? Well, the way you want to think about it is that, there is a probability that comes from geologic risking, right? And now you go and say that I observe an amplitude, okay? And I know that that amplitude is roughly consistent with oil, okay? Now when I go, given that observation, okay, how much do I have to change the probability to update it, given the observation, what is the probability, okay? And that ends up going, if the observation is consistent with what you want, it increases the probability. If the observation is inconsistent, you get a negative boost. I don't know. I mean, it's an abuse of the language, you know. And I called it, the DHI suck factor, in the case if it wasn't what you expected. But, normally no one will go and present a prospect which has a negative boost or things go negative. And since you always saw positives, but it was kind of interesting, after we started doing this, you realize some of the things that people were presenting from time to time actually were negatives, and it went down, okay? I mean, does that help?
I guess so. I guess before boost is, let's pretend it doesn't have an amplitude.
Right.
And when we recognize it as an amplitude, we add a boost.
That's right.
To it, recognizing that amplitude conforms to a structure or what have you, or a positive AVO.
Exactly, right. And I think that what we talk about is, and the main thing of the course is, how can you be quantitative about what that boost should be, okay, in a repeatable fashion. So if you did this 3 years from now, you would get the same answer that I got today, or roughly the same answer that I got today. And also, if you compare it to drilling results, you get results like you saw earlier. Any other questions? We also have extended this to include AVO and not only amplitudes. And we'll get into this spreadsheet. I don't expect you to read all the little detail here right now. But to note that there are different steps in here, and we'll go and work you through this workflow. And what you're going to do is you press this, and it does that, okay? And before you press this, you need to fill in the yellow stuff, and you end up getting the red stuff on the right. Okay, and those are the things you should look at, or these other cells here end up being the outputs of that, okay? And so this is how we're going to walk you through the workflow, because the spreadsheets themselves document the workflow. And I just sort of showed some of the examples of some of the cluster plots, and we're going to get into that in a later lecture, but the fact that we look at things like near and far, or the idiosyncrasy of the way that we do things. There are reasons for doing that, though. And but again, we'll get into that a bit later. But in the end, you still get these probabilities. You still get boosts, but you now are using like amplitude variation with offset. But if you now ask, okay, why should I care about this if I'm looking at coal? Okay, why AVO? One thing you end up finding, though, that you probably realize, coal is really rigid, but it's pretty darn light, okay? And so because of that, it ends up having a fairly unique sort of shear properties, and because of that, it has a very unique AVO associated with it. We can talk a bit more about that offline, but we do worry about that from a petroleum perspective because it's actually something we don't want to find if we're drilling a well. But, and so that there is some knowledge associated with that. And sort of what are the inputs and outputs? What do we need from you, okay? We need to have the nearby wells analyzed by a petrophysicist such as Mark Block here, and also QI specialists to drive the end member lithologies. I think that a particular view is that it would be better to even have these end member lithologies and these particular trends derived by the petrophysicists. Because I think those of you who are familiar with the particular within Shell, but they do not allow QI specialists to derive the end members. Those are actually derived by the petrophysicists. The seismic data needs to be processed to, in quotes, a gold standard. I'm not going to go into that, but I mean, one thing that you find fairly commonly within the petroleum industry is what's called spec data, okay? And sort of what's spec data? Well, spec data is stuff that's sort of acquired on spec, but it's also processed in a way, it's shoved in a workflow so it looks pleasing coming out and takes the minimum amount of operator intervention on it, okay? But there are particular things that are done into that which really do destroy the fidelity of what the amplitudes are, okay? And so that a lot of information you could have gained from it, you can't, okay? That's one thing I want to talk about, because the particular workflow I was looking at, in the Karuna data, is much closer, is very close to what the standard spec workflow in petroleum industry. But Dave and I will sit down and talk with you about that.
Just a quick backstep, Mark.
Yeah.
In member lithologies, they're talking about the
Sand, shale, coal,
and the
volcanic.
uncertainty in determining that for well logs in well portions.
Well, that we go, and when you say end member, we're going to get into this in a lot of detail, and that's actually something that's sort of BHP specific in terms of the concept. Again, if you come from a shell area, this is not. I mean, it's borrowed, from a concept there. But you go and you'll say, what is the good sand? If it's 50%, laminated sand shale, then what we want to know is what the good sand would look like and what the shale end member would look like. And then we go and use other methodologies to mix them together, which Dave will get into. Okay. Well, I'd wait, and after we go through the laminated mixing lecture, if you still have a confusion about what an end member is, we'll make sure that you bring up the question again, and we'll make sure it's addressed.
On the seismic data, gold standard, if the target is not imaged properly, like subsalt targets where there's a lot of ray pass gathering, you're not getting near offsets, or you're just getting us an uneven offset range on imaging.
Right.
A lot of this won't work because it's like having bad seismic data. You're not imaging the
That's
target.
right. Well, the first thing is you need to image. Then, if you can go and start getting a good image, can we go and get it to the point that we can do amplitudes? But a lot of times sub-salt, if the salt is simple enough, even though you're going to not have long offsets, so you're going to be doing normal incidence reflectivity, you have to live with that if it's simple enough, and if you're using the right algorithms, that you can go and possibly start getting some amplitude information. But I do agree that, first get the structural image, and then, you can start asking questions of, can we go and take enough care to be able to get the quantitative interpretation. But you also will go and see, when we get to the risking part of this, that we ask a very simple question: should you trust the data, right? And if you can't trust the data, that means that you get no boost, okay? Neither positive nor negative, and that, and many times people will go and get data that's not processed correctly. They'll see something positive, they'll say, great. No, if it's not, that's just probably dumb luck, okay? You should ignore it if you're in that particular case. And you've had to go and do some things just to barely get an image. What you got is barely an image, and don't, trust it beyond that. So you need to worry about that. And I think that some of the areas in nickel, for instance, that we probably will be just, looking at, if it's complicated enough, just how do you get the image? And then it's just going to be trying to estimate things like structural uncertainty, or, what is the gross package. You're not going to be able to get into these more subtle things. With coal, and shallow, you get a good image, and then I think you should be able to go and be, making some of these statements. The next thing is that we also ask for basic interpretation, and also sort of a high grading of what the particular prospects are. Having top and bases are good, and to have sort of the laterally continuous sequences interpreted. In other words, that geologically things like sequence boundaries or sort of ubiquitous shales that you can easily follow and are actually very good things to have. And you'll see the ways that we can use those as edge picks in order to be able to understand what the sand is. Many times that's much better than trying to pick the sands, okay? So having a good sequence, boundaries ends up being a very good input for us in most cases. and is probably what I would suggest picking. It's easier to pick, and we'll talk about it when we do the amplitude extractions of why, you know, that it ends up even working better for the amplitude extractions. What are the products? Well, first of all, we'll tell you what type of AVO or amplitudes you should expect. We'll go and give you a wavelet derivation and a sparse spike inversion, trying to spectrally restore the data, or many times people say we'll increase the bandwidth of it, and many times it is what happens. We'll go and extract the amplitudes and areas, and we'll go and transform these into risk and volumetrics. And it really is, though, a cooperative process with the asset team, and it's something that I actually encourage much more of this being done by the asset team members themselves. You know, the people like yourself, Angus. You know, you should be able to go in and be extracting or seeking amplitudes and working through some of these spreadsheets on the fly in order to be able to understand that. And I think it's been identified as a goal that, again, someone like yourself, you know, Rick, that you just go in and can work these spreadsheets, extract these amplitudes. And you'll see where you try to get the tools and the shape to do that. Some of the more phase 2, these model-based inversions, are probably going to remain more in the hands of the specialists, at least for the sort of the midterm. And this is sort of part of the ownership, that, you know, you can't make decisions if you aren't really involved with it. Now, what's sort of the workflow and sort of what's the software involved with it, okay? Well, here are the different steps on a large sense that we go through, and on the right are the pieces of software, okay? And as we go through this course, okay, I'm going to keep bringing this up, and I'm going to be pointing to say we're doing this now, now we're doing this, now we're doing this. Okay, here's the spreadsheet that we're using as we go through this, okay? So this is sort of your high-level roadmap. I have a copy of it, you know, in the exercises, and I would even suggest ripping it out and keeping it out there so that you can understand where we're going. Okay, first of all, we do this petrophysics to understand what these end members look like. Mark Block here has developed a tool to help with this, and you'll see why when you do the exercise, because you'll say, I never want to do this again, can't we automate it? And Mark did, okay, because he felt the pain. Then the next thing we do is we derive trends with uncertainty, and that's done in a spreadsheet called LFP analysis. We determine what the expected AVO or an amplitude response should be. That's where we do all these Gaussian substitutions. That's in something called the rock physics spreadsheet, and we're going to be putting our hands on that. Then we can do multi-stat, multi-well wavelet extraction. We're not going to be talking about that. John Hedich over here, though, will be getting intimately familiar with this. There's a code that comes out of CSIRO that we use to do this. We do consider this sort of a key differentiator in terms of technology, and I'll talk more about it and why we found it to be of advantage. We can do multiple stack AVO inversions, both model-based as well as sparse spike, and I think I'll show that we have methodologies that have superior performance in ways that matter compared to other things out there in the industry. Also, we have license to use it throughout BHP. So that's another thing to note, Jeff, is that you know, we really do have some really high quality sparse spike inversion. And if you go out and try to buy something from like Jason Geophysical, it's about a $200,000 package. And we have something which you'll see the benchmarks have superior performance, and it's effectively free. Well, you have to learn how to use it. We also are going to be training up some people to help you learn that. And also, Long is quite experienced at using it, for instance, right here in petroleum. Okay.
Mike, those names in black on the right, those pieces of software, are those all BHP proprietary pieces of software, or some of those purchased outside?
Right now, that the things that I've talked about are These are BHP proprietary, even though, I mean, I'm not naive. These things are actually all over the Australian petroleum industry. I think there are a few companies here that don't have their own copy of them now. Part of it is that, like I said, I've almost did this as a joke. It's not really a joke, but the picture, you know, of the last time I taught this in Perth and having the person's current company logos on top of it. So it's ended up being, the particular approach actually down here in Australia that I'm talking about has almost become the norm, I think, in this country. So.
To that, I've sat in data rooms and there's been icons on the desktop that are the BHP logo to launch the BHP software from.
Well, it turns out that we've ended up open sourcing the viewer, but yeah, that is true. That they sometimes haven't even removed our logos from it. The stuff around the CSIRO stuff, this actually was developed underneath the agreement with the National Laboratory where it was open source. And so this stuff you can download from the internet. This particular package is proprietary to BHP. Let It Wave, which was just bought out by a firm in Silicon Valley, actually holds the rights, but it hasn't been sort of adopted or used by other particular people in the industry. So when I get to this, there's an interesting story around it, what the real use and market is, because that company was bought out for about $80 million, largely based on the inversion technology. Now, I'll think about what the use of the inversion technology could be, but you'll be surprised, I think, when you realize it. But you also realize why they were bought out for $80 million. And are quite happy. They're sort of continue to be good friends of mine because of, I think, some of their riches. But actually, no, we had a lot of fun working together. Then we get down to the seek and amplitude extraction. That's done on the workbench.
Is that proprietary?
Certain parts of that are open source. The particular plugins that go and do this are proprietary. We decided that the viewer isn't something that is special to us, but things that embody the workflow are, so that ends up being proprietary. And you'll be playing with that amplitude extractor. And in fact, it can go directly into Landmark, for instance, and extract amplitudes from Landmark and put them into Landmark.
So it's not a JSON product, that's secant amplitude area?
No.
Okay.
I mean, the particular thing, I mean, it dates back to Shell and a lot of work that was done there. And we'll talk about why we like secant amplitude in a lot of pretty gory detail over some of the RFC interpretation, both in terms of qualitative as well as quantitatively. Why? You know, for instance, I always will what's called run some data before I'll interpret it. I just find I just can't interpret RFC data that way. The next thing is we end up normalizing the amplitudes to the expected responses, and that's in a spreadsheet that we have, and you'll be using that spreadsheet. That's actually a workflow where I was showing you where I pressed all the buttons in order. That's this spreadsheet right here. We have a version for AVO analysis and a stripped down version if you only have amplitudes, because there's no reason to have the more complicated stuff if you're not doing the AVO. And then we go and given, first of all, what the prediction is, then given what the answer, what the observation is, those two are combined together in the risk analysis spreadsheet in order to come up with these integrated probabilities, or those wheels of fortune, that's sort of what we call them, that you saw at the beginning. And also you end up getting a net sand estimate out of the secant areas, which is like an amplitude thickness. Okay? We'll be coming back to this again and again and again. So hopefully by the end you should be in a position where you can explain this to me. Okay, sort of this is more of a particular data flow chart as we go through here, okay? But anyways, so that now you end up having from this upper branch ends up being your prediction. The lower branch ends up being your observation. Compare observation to prediction in order to get probability. Okay? But again, this is going to be another one as you go through the exercises to follow through to understand what the data flow is, okay, and where we are in the workflow. This is the particular workbench, and the one thing that you'll see about it is that it's web-driven. You'll go to a website. You can go and have what are sort of landmark sessions, but you can have an icon that you click on to restore that session. And I'll go and talk a bit more about it when we get to amplitude extraction. Here again is sort of the web page you go to. You click on this link. Up comes a particular selector where you say what's the server, whether or not it's Perth or Houston, where the data is at, what the data set is, and what sort of the session name was that you ended up saving. Then we have a project selector or sort of a project manager so that you can go and sort of see what all your data sets are. You can actually drag data sets over to the viewer to view them, for instance, that are in your project. You also end up having saved within your desktop different sort of viewer sessions that you can open so that something before or after the let's say an inversion or an amplitude extractor. You can also open up an amplitude extraction, so you can have 8 or 10 different amplitude extractions that you've done here and what the parameters that were used in those amplitude extractions. We sort of talked about spectral decomposition. This is what you would click on to do a spectral decomposition. And you'll keep, the parameters associated with each spectral decomposition. And also, you can also go here when you do the amplitude extraction and spectral decomposition, go directly into and out of landmark, as well as some more common data formats. Another thing for the mining people to note, that this is a generalized sort of 2D seismic viewer as well as sort of event picker. It is BHP software, so again, the marginal cost to us is zero. Other than obviously the time you spend learning the software or installing it. Okay, and now we're just getting to the outline for the course. First of all, we're going to talk about factors affecting rock velocity. We'll talk about multi-phase pore fluids, and for you hard rock people, I've said, that's not really of much interest. The acoustic fluid properties and fluid substitution, again, for hard rocks, you don't have pore space to substitute fluids into, so not much applicability there. Trend curves and rock properties, those actually do matter. And that's how you can tell one rock from another. And I sort of gave that coal example as, that is, distinctly different. It tends to be more like a sandstone is for us. It would be unnaturally competent for its weight. Okay, so those are important, okay, for hard rocks. We talked about how to combine different rocks together. Then we go into, and this is probably a little bit more for the petroleum people here too, is how can you tell how much the rocks have been squished together? And that can actually come from seismic imaging velocities. In other words, you have a velocity that you needed to have to make your image. There's a lot of information associated with that, okay? But also this does have an implication for hard rock people, because if you go and have a formation that's a lot harder than another, you'll be able to tell that you need to use a different stacking velocity for that. And so that actually can give you independent information to the reflectivity of whether or not you end up having let's say a harder rock in that area. They're all hard in that case, but some of them can be harder. The next one goes about how do we go and calculate what the theoretical seismic reflectivity is, an AVO. How do we extract amplitudes in ways that we can make sense of? How do we estimate risk? And that's where I tell you all about bays and have a little quiz on it. We talk about well ties and calibration. And then finally, the need for the next level of quantitative interpretation down here where we talk about that phase 2, the model-based inversion, where we relax some of the constraints. And then finally, we go into lease sale, which is a South African wine country, because all the prospects were named after wines, is the reason why. Exercises, quite a few. We go through the whole workflow and all the different spreadsheets. I'm not going to go through those right now. And then one final thing about the structure of this course, okay? At the end of every lecture and at the end of the course, we always go back to what are the 1 or 2 things that you need to know, okay, that we've talked about. Because I've droned on now for a good hour and a half and probably say, Mike, shut up. But what do you need to know, okay? Okay, we use here a Bayesian approach. It gives you risk and volumetric estimation. It's been endorsed by petroleum leadership, okay? And it's been calibrated with look-back study, okay? So we've been able to predict what reality is, and our management endorses it, okay? What's the next thing? Okay, it solves a problem in risking that our competitors have with the principle of minimum accountability. And that can lead to probable competitive advantage. And that's the reason why we got this. And this particular method is embodied in the workflow, and it's that workflow that you're going to be learning, through the rest of this, 3.5 days, okay? And I think that, yeah, it's just about time to head down.
Let's break it here.
Yeah.
One last comment is about structure. The way we try to do things is to talk about the simplest things first. So you will see simple models and questions will occur to you, so oh boy, that's awfully simple. My reality isn't that way. I've seen a lot of logs, or I've seen a lot of stratigraphy or whatever, and I don't believe in that assumption. Okay, well, you can ask a question, but if I should respond or Mike should respond, hey, we'll talk about that later, take us at our word, because we try to proceed from the simplest and then we try to add complexity gradually as we go along. Okay? Okay, having said that, I'm going to try to talk about some simple preludes here, a bunch of definitions, review for many of you, things you probably learned in school or in BHP. I think this goes down a little bit if I can find it. The classical exploration questions that one wants to answer. You win a lottery and you decide that oil's really going up, but the value of the Aussie dollar is probably doing well. The value of the American dollar is going down. So I'm not sure I want to put my money in a bank at this point. It'd be better if I had an oil field or a coal field. And for oil, at least, the classical method of exploration would be to try to answer the following questions. And you would get yourself different technically trained people to answer these different questions. The first would be, do I have a source rock and a charging mechanism? Is petroleum ever generated in a place where I'm considering drilling? The second is there a reservoir rock and potential seal? You might have source rocks very deep. You might have metamorphics over them, and so even if you ever were to drill into such a section, you might never be able to produce the rock, the oil that's there because the rock's too tight. So you have to have those reservoir rock and potential seal. Who would you get to answer this question? Well, that's a geochemist. Who would you get to answer? That's a branch of geology, a special branch of geology. Who would you get to answer this question?
Geologist.
Yes, that's stratigrapher in particular. Right? And then the last thing is there a trapping geometry? And of course, that's where the geophysicist classically has come in. Shoot some seismic, try to map events, determine velocities, and get the structure of the beds. and see if there's a closure up against a fault or four-way closure or whatever, or traffic geometry. A shortcut to try to short circuit all those questions at one time, that is quantitative seismic amplitude interpretation in certain circumstances, and it will provide evidence that you have all three of those components if you have the clues and the right geology, the right characteristic of rocks in your section to be able to observe the effects and interpret them. That's what I hope to convince you of. That's what this says. And when and how, I said in certain circumstances in the previous slide, well, you know, what are those circumstances? When is this applicable, when is it not? I'm talking from a petroleum standpoint. So I'm going to come back to this slide later, but this is a cartoon of a 2D kind of profile. So down here we're looking at a cross-section of the Earth with some structure that comes up dip, and you have a reservoir rock in here. Up here is a hydrocarbon saturated sand, let's say, and down below it a brine saturated sand. What might you see on the seismic if you have properly calibrated it, etc.? Well, you might see something that had a low amplitude over here where there's brine, and a higher amplitude where there's hydrocarbon gas in particular. And we'll get into the structure of this curve and why that might be the profile that you would expect to see. 3D, of course, just carry this around in some sense. If you had this situation here, you might expect to see something more like that. That is a lower amplitude response from the oil than from the gas, and a higher amplitude response from that, but still higher from brine and higher amplitude from gas. Why you should see these profiles, that's what we're going to talk about for the next day. Here's some definitions. This is sort of a jargon. It's useful to know during the rest of the discussion. And so let me just start with simple things. We won't talk about compressibility in all probability, but it's the easiest thing to understand, perhaps, something that's important. What is a compressibility? Well, its definition is that it's the fractional change in the volume of a body, a plastic body, in response to a certain applied stress, or per unit of applied stress. That would be hydrostatic stress, hydrostatic pressure here. Fractional change in volume. And we have a minus in front of it because obviously if you apply more stress, higher pressure, you reduce the volume. So D volume is negative. So in order to make it a positive number and not have negative numbers all over the place, we just simply reverse the sign for that. What's the J mean? Well, you could compress a material in different ways. You could compress it isothermally at constant temperature, or you could compress it isolating it from the world thermally, adiabatically, if you like. One of interest to us comes out to be the adiabatic compressibility, as that's the one that relates to the velocities of sound in elastic bodies. The units of compressibility are what? Units of volume cancel, so you have units of inverse pressure. Sometimes you will see compressibilities quoted. The easiest experiment to do is isothermal, not adiabatic. So commonly you'll see isothermal compressibilities in the literature. You'll see compressibilities, and they will be often quoted by engineers in terms of microsips, because that is supposed to be for inverse PSI, 10 to the minus 6 inverse PSI. So if you see something like that, it's a sip. Just don't worry about it too much. Bulk modulus. This is something we will talk about a lot. And what is bulk modulus? Well, pretty simple. It's 1 over the compressibility. It's inverse the compressibility. So what is it? It is a stiffness of the elastic body to compression, to applied stress. The one-dimensional analog of the bulk modulus is a spring constant. when you took your first physics course, one-dimensional springs and dashpots. K was the spring constant. That's what this is. Its units, obviously, therefore, are pressure. Shear modulus is the next little thing we'll talk about. Sometimes denoted U in me, and other parts of the literature. That's older literature. More commonly these days in the literature, you will see that represented by a G, a capital G. Shear modulus is well, what is it? If I try to deform a body by placing my hand on it and pressing in a certain direction, let's say the K direction, that is the ratio of the pressure applied to the body, well, not the K direction, it's on the indicate direction to the face that has the normal in the L direction, where K is not equal to L. So that's a traction this way. The normal to the table is vertical, that's L. K direction could be this way or this way. Okay? And what is the strain? E is the strain. The strain is a length really divided by the initial length. The length due to the deformation is the length times d theta, if you like. There's actually a deformation of the body in this direction if I put such a traction on an elastic body. And so this is just a dimensionless quantity. So this too has the dimensions of pressure. This 1/2 here is just a scaling constant. It makes the strain tensor unitary and people like that. That's useful. So remember, this is the important part. We're talking about that. The applied stress in a direction perpendicular to the normal of the interface to which it's applied. Okay, Young's modulus is very much like this, except that it's the same direction. So now we have, I wrote it differently, and again we've got the minus to make it positive, but if I squeeze on a body, an elastic body, let's say this thing, in the same direction with an isostatic stress, I mean a single not isostatic, but one-dimensional stress in the direction of the length of the body and measure the fractional change in the length of the body. That gives me the Young's modulus. This again, we don't use, but you'll see why I wrote it down, because again, this is an easy experiment to do. So these kinds of numbers are easy to find in the literature. Okay? And you'll see that these numbers can be connected with those. Okay. That too, therefore, has the dimensions of pressure. And finally, I've written one down here called the Poisson's ratio. Poisson's ratio, there's a lot of ways you can write it. But basically what it is if I squeeze on this baby, and it has a certain length, and I squeeze in this unidirectional stress, with this unidirectional stress, and then I measure the deformation this way to that elastic body, take the ratio of this deformation to this deformation, of the incline deformation. That number is just a number. It has no units. And that number is Poisson's ratio. And Poisson's ratio has limits. For a fluid, obviously, that would be 0.5. It goes up to 0.5 because it'll squeeze half in that direction, half in this direction. For a perfectly rigid body, which does not deform when you put a load on it in the perpendicular direction, it would be 0. It would be the ratio of 0 deformation to a finite deformation, so it would be 0. This is dimensions. Well, here's some facts about elastic bodies. Simple, isotropic, and homogeneous elastic bodies. What's isotropic? Same in every direction. A property, you got it. The property is the same no matter which way you look in the body. Homogeneous means the body is the same everywhere. The air in this room, we presume, is homogeneous. Okay. Also, the elastic properties of the air is isotropic. The air really isn't homogeneous, but we won't get into why not.
Seems to be a little bit hotter near the front.
Yeah, right. There's a little more hot air coming out here. Okay. For any such elastic body, you only need two elastic constants to describe all of its elastic deformation, and you can choose any two you choose, any two you wish of those that we talked about just in the previous slide, and others as well. And then you may convert from one pair to another pair if you so like. Only two kinds of body waves are supported in an isotropic and homogeneous elastic medium. One is a compression wave, which I'm going to denote VP. That's the one we normally use in seismic prospecting. And the other is a shear wave, which also is used sometime, but not very often. The compressional wave has deformation, as you will remember, in the same direction as the propagation of the wave. So it's a compression and a rarefaction along the ray path of the propagating wave. For the shear, the particle motion of the deformed elastic body is perpendicular to the propagation vector. So there are two kinds of shear wave, one with this vertical polarization, and then one with the horizontal polarization. But for an isotropic elastic body, it doesn't make any difference. There's only one shear velocity. Both shear waves, both polarizations of shear wave travel with the same speed. Okay? Here are relations. Don't worry about this over here. Oops. What about
You went to select, don't worry about it.
What?
You know, just
That?
Correct, don't worry, just keep talking.
Okay. Let's just look at this one first. The rho VS squared is equal to mu, the shear modulus. That's pretty simple. Don't need but that one modulus. There's a plane wave modulus called M. That's K plus 4/3 mu. You can always write it as another modulus. Rho VP squared is equal to K plus 4/3 mu. That's true for any isotropic homogeneous elastic body. We could write this, convert from one system of elastic constants to another pair, if you like. For example, Poisson's ratio and bulk modulus. You'll see more of this particular pair, and there's a reason. This is the particular conversion for the general elastic body. I already talked about this. Poisson's ratio is limited 0 to 0.5 for real media. And what would happen in the case of a liquid? In the case of a liquid, if I do this on a liquid, what happens? It doesn't stay together, it just slips. So I don't have any shear modulus. Shear modulus is 0, so this goes away. And this goes away, there is no shear wave. Only one elastic wave propagates. That's the compressional wave. And its velocity, or its velocity is given by the bulk modulus over the density squared. Okay. Here's a table. You can see it here in your book. If you get a magnifying glass, you may be able to decipher it, but it's on the website, so just look on the website. This would give you the conversion. If you see constants and you want to get, let's say, the shear modulus in terms of, what we got over here, Lemay's constants, lambda and mu. Well, that's a bad one, shear modulus. Poisson's ratio in terms of lambda and mu. Here's the formula that would give you Poisson's ratio in terms of lambda and mu, which are Lemay's elastic constants. So that's all that is, a conversion. You should realize that the velocity ratio, VP to VS, is another one we'll talk about sometimes, R, and it is simply related to the Poisson's ratio. Poisson's ratio is monotonically related to the ratio VP to VS. And that's a dimensionless ratio too, and this thing will tell you how to do that. So anytime you want to make a conversion, you can do that if you like to express things in different characterizations.
Yeah, and let me just go and just put another sort of accent on that, is that, isotropic, homogeneous media, there are two numbers that matter, and you can always go pick two and translate to any other two in a straightforward mapping. And you'll see though, I think there tends to be a lot of to-do in the literature about exactly what those two parameters are. And I think that to a large extent, things separate well, sometimes more linearly in one rather than the other. And we'll actually talk a bit later about, what are optimum, sort of parameters or two parameters in order to discriminate things. And I'll sort of defer it till then, but unless you go and start looking at, and I'll sort of leave up to you too, what do you think in the end is going to be the thing that will cause you to choose one set over another? And just sort of think about that, and I'll get back to that question later on.
Okay. Normal instance reflection of plane compressional waves. Well, that's starting from ground zero, right? I have an input wave, plane wave, on a plane interface between two isotropic and homogeneous elastic bodies, which has an amplitude A0. That wave has an amplitude motion A0. Only two waves leave: a normal wave reflected and a normal wave transmitted. Why is that so? First of all, the two media are characterized by their own densities and velocities, and we're only going to consider here the compressional wave, so I'm not worried about the shear wave velocity, which would be the second elastic constant. I would need here a second elastic constant. Continuity of tangential displacement and stress makes it impossible to generate a shear wave at this interface. I have no tangential motion. If I don't let this surface, if I don't let the upper body slip with respect to the bottom one, and I have continuous stress across that boundary, then I can't generate any shear wave. Snell's law requires all emitted waves to be normal. They can't come off this way, that way. And continuity of normal displacement and normal stress will give you these two ratios of the amplitudes of the reflected wave to the incident amplitude and the transmitted wave. And the ratios, those two ratios are called reflection coefficient and the transmission coefficient. The amplitude coefficients are also energy coefficients, which are squared. The result is that the normal incidence of P wave reflection coefficient at a plane interface is given by this expression. R, the 0 stands for normal incidence, 0 degrees angle, is the difference between the acoustic impedance of the lower and upper media divided by the sum of their acoustic impedance. What's the acoustic impedance? The product of density times compressional wave speed. This can have either sign. I could have just as well written ρ1 minus ρ1 v1 minus ρ2 v2, but once you choose a sign, you must stay consistent with that sign. And what I'll talk about, we're going to take the lower less the upper. Pretty simple looking expression. Let's talk about what that simple expression results in. Suppose I have my nice hydrocarbon-filled sand up here at the top, and down the dip I have a brine-filled sand. There's a lot of things we might be interested in, but suppose we were able to get a measurement of the reflection coefficient at the top of this reservoir, over here where there's hydrocarbon, and we'll call that R sub H, and another one down dip from the same stratigraphic unit where it's brine filled. And suppose that the properties of this overburden medium, the row 1 and the VP 1 of this shale or whatever it is, salt, whatever it is, sealing rock, does not vary laterally. Then it turns out that a little algebra from that previous expression will yield the following result. R sub H minus R sub B is approximately, which I'm going to call delta R, is approximately equal to minus the reflection coefficient at the fluid interface in the reservoir rock. So this has got the opposite sign to this difference and is approximately equal to that difference. What that means is that so long as this thing doesn't vary laterally over my reservoir, I don't need to know anything about this. If I can make those measurements, all I have to do is to know how things behave in the reservoir rock. And you remember that logic slide Mike showed earlier this morning before we all went down and got inducted? He showed the logic slide and said, well, we're going to make calculations. We're going to try to make measurements of amplitude, connect the two, calibrate them, and compare the two. This is important for that. The thing you need to focus on, not that it's the only thing you need to focus on, but one important thing you need to focus on is what happens when we change fluids in the reservoir rock. There's another little factoid of great value sometimes, and that is the reflection coefficient can be thought of, the normal instance reflection coefficient, as the derivative of the logarithm of the acoustic impedance function. It's just a difference in a function divided by twice that function value, right? The average value of the acoustic impedance. So I can write that as R0 as 1/2 derivative of the log. What's the derivative of the logarithm of x? Dx over x, right? So that's what we have here, the derivative of the logarithm function. It can be expressed in time, it can be expressed in depth. So if I integrate both sides of this expression, I flip it around, but if I integrate it, what do I have? I have the logarithm of rho v is equal to 2 times the integral of the reflectivity. So if I have a seismic trace and I processed it and simply gotten reflection coefficients out of it, I mean processed it to where all I have left are reflection events, and their amplitudes are proportional to the reflection coefficients at the rock interfaces in the subsurface, then when I integrate the trace or run sum it, what is an integration? It's the sum of all the reflection coefficients in the trace.
Or the running sum.
Yeah, running sum, that's what we call run sum. If I then run sum it or integrate it, I get the logarithm rho v divided by 2. Well, why is that useful? Why would you think, oh, I did it again, I'm sorry, Mike. What did you do?
You hit the menu, you just hit the return button.
Return?
No, it's not on there here.
Oh, return button?
Yeah, I mean, it's on there.
Why is that useful? Well, you guys have all looked at logs. You got a density log, you got a velocity log. You're used to looking at what a log is like. And you know that in certain stratigraphy, the velocities, the transit times, and the densities will show the difference between different lithologies. So when you perform this operation on a seismic trace, what you get is something that looks like a log. You have to band limit it, of course, back to the seismic bandwidth to compare it. But you get something that looks like the physical properties of the Earth that you're used to looking at. It'll be related to other kinds of logs too. It'll be easier to recognize stratigraphic units in this case than in others. And that's one very nice reason to remember this relation.
I mean, so I had a picture over here too, and I'll try to, when I sort of jump in, every once in a while Dave is talking, it's really to try to highlight probably a very important thing, okay, in terms of practical use, okay. And I sort of drew up a little picture here that sort of shows, first of all, something that would be like a density log, that is something that you'd acquire, okay, with the downhole tool. Unless you're in Nickel West, because they don't like to put radioactive sources down the hole.
But in petroleum, in potash, we tend not to have that safety quality. The second thing is the density, which comes from a sonic log. And, well, you can go and do some very simple math, which is to multiply the two, in order to go and get the particular acoustic impedance log, okay? Just multiply the two together, and then you go and take a logarithm of it, okay? But the one thing to note, and I have sort of shown in a little tiny thing here, or maybe you can get out your magnifying glasses or binoculars, but if I go and have a sand, which is just a block here, that tends to be soft in acoustic impedance, okay, that will just sort of show up here as, let's say, this little block, okay? Easy to interpret. Let's say if it gets less sandy near the top, it'll actually sort of come back in this fashion, okay? It'll sort of go out and then come back like that, okay? Now, then if you go and say, well, how do I go and understand what the seismic trace or the RFC or the reflection coefficient trace will look like? Well, if I take the derivative of this and then band limit it by sort of, let's say, applying a wavelet to it, I end up getting what normally is your RFC seismic, okay? But the problem that you have with this is whenever you take a derivative of this, you take something that's a nice block, now you complicate it by making it a spike at the top and a spike at the bottom. And then what happens if I go and have something that comes up and then is a gradation coming up, okay? It's about that point in my basic interpretation course, my head started spinning and I just said I'd give up, you know, especially if you add a couple sands and different profiles on it. I mean, my mind, for whatever reason, can't differentiate very well. And so that I always found it easier to try to interpret something that ends up being much closer to the log trace, okay? And how do we do that? We take the seismic reflectivity, and if we integrate it or take the running sum, we end up getting something which is closer to what the log looks like, okay? And there's actually another more quantitative reason for doing this, and we'll get to it later, but it ends up being better even in a quantitative sense to do this if you start doing the pay estimates.
You'll see that lecture.
So the integrated trace, the top of the sand will be a zero crossing, the face of the sand will be zero crossing.
It is correct, yeah. And like if you have a finding upward sequence, you'll see it's a backward loaded wavelet almost, okay? So you just tell immediately if it's a finding upward levee, for instance, right? Where I've always found it much harder when I started
Yeah, if you look
trying
at,
to get into RFC.
if you do a simple exercise sometime and you look at it's the spikes, I'm showing you here, these. Here's your log rho v, and over here is the differential operator. So this would represent the two spikes you would have at the top and bottom of this thing, and then you convolve that, or band limit those two, and look at them. What you will see is that it's when the thickness of the unit is relatively small, that is, when it's not resolved, the top and bottom are not resolved, you will find that it's much more difficult to see that you have a unit there and to understand what loops of the seismic mean in terms of stratigraphy. That's what you will find out. That's what we're talking about. Okay, where are we in this logic slide? What have we been talking about? Well, here it is, right here. What we're going to do is look at the seismic traces and make amplitude measurements, and we're going to calculation. The next thing we're going to do is talk about rock characteristics, and we're going to talk about all about this thing. How do we get this calculation? That's Gossman, etc. So that's the next topic that comes up. So what's important here? I mean, this is sort of a hodgepodge of the basics and review and things like that. Quantitative seismic amplitude analysis can short circuit the whole logic, normal exploration logic, in certain circumstances. You're going to see what those circumstances are. And if you're the guy that's in the corner office making decisions, let me tell you, you're operating always in a world in which you have less information than you want. So it's awfully nice to not have to answer each one of those questions independently and to have confidence in the information or should I say this, the idea of the decision that you will make as to whether or not to drill, as Mike was showing you earlier about your DHI indicators and the ways you have for updating your DHI routes. Normal instance reflection coefficients depend on the densities and velocities of the rocks involved in the reflecting interface. Gee, that's nice. Compressional wave, I should have put in here normal incidence compressional wave. Well, it's okay. The shear wave, same thing. It's the shear beams, density and shear velocity in that case, normal incidence. The lateral change in R0, the normal incidence reflection coefficient, is equal and opposite to the normal incidence reflection coefficient at the fluid interface and reservoir rock. That's important. We only have to really consider in determining when this is going to work. We don't really have to consider when I'm going to get big effects at the fluid interface of the rock. That may not be what I measure on the seismic, but that's when I'm going to see measurable big effects. The reflectivity trace is equal to the derivative of the logarithm of acoustic beats divided by 2. We just talked about that. And we're going to have to calibrate the reflectivities. You saw the logic slide. You've seen it already twice.